When we do data analysis or machine learning, there are two main types of approaches. One is called supervised, and the other one is called unsupervised. So supervised learning is when you have some response values available. So for example, if I want to predict house prices in Boston, and I have tons of data of how many rooms a house has, how many bathrooms, how much area, how much living space, which zip code, how old it is. So if I have a lot of data and also like prices, then we can develop a model, and that process is called supervised learning. But there are many cases where you don't have a response. You just have many variables and you try to do few things. So that approach is called unsupervised because there is no response variable. So cluster analysis is one such example of unsupervised learning. It is a very important technique. I have also listed this as one of the 10 must-know machine learning methods because there are cases where you'll have to deal with situations where there's no response variable. So the main idea here is, or the main goal is to form groups or clusters of similar records. We'll see what is meant by similar, because similar is something we have to capture with a method, like some kind of measure of distance, and then say that, okay, these two things are similar because the distance between them is less. And these two things, like two companies or two groups, are different because distance between them is big in terms of many variables. So we'll look at like how to figure out what is similar and what is not similar, but that's the main goal. Form clusters or groups using some measure of similarity. So this is used for segmenting markets into groups of similar customers. Like you may classify your market in different ways, like high income, low income, middle income, or young, old, or middle-aged. So every business basically tries to cater to a specific market, and they identify like which group they are serving, and cluster analysis can help them in focusing on their customers. There are so many examples, not only from business, but science. You must have seen in your high school periodic table of elements. Two elements which are closer together in the table, they are very similar. And two elements which are like further away in that table, obviously they are not similar. Classification of species, grouping of securities in portfolios. If you have a lot of money and if you want to invest with some investment company, typically they will offer you that, okay, these are like risky assets, these are like high income, these are where you can get a lot of dividends. They group securities or portfolios based on certain type of groupings. Another example is like in army, there are so many people, and it is very difficult to create uniforms or dresses which are like customized for each and every person. So that's not feasible. It will be too expensive, too time consuming. They have done cluster analysis and identified some groups, and then they make these uniforms only for those identified clusters or groups, which covers almost everyone. So that saves a lot of time and also like money. These were just few examples, but we'll look at one specific example today. There is a type of clustering called hierarchical clustering. Just like in a business, there is a hierarchy. There is an operator, supervisor, manager, director, or like CEOs. Hierarchical clustering basically looks at clustering at the different levels. If you look at 6 companies, A, B, C, D, E, F, and suppose distance between them measures something about some parameters or variables and converts them into some kind of distance, then we find that distance between A and C is very less. We can make first cluster by grouping these 2 companies together. Similarly, B and E also have less distance, so probably that can form the second cluster. If we allow slight more distances, then you can see D is close to B and E. So this circle has 3 companies in it. So it starts with like 2 goes to 3 and then so on. by the time it reaches cluster number 5, every company in the circle is part of the cluster. So this is like one big cluster and everybody is part of it. This type of going from like one level to other level is called hierarchical clustering. So you start as if every company is its own cluster, then try to group together like two similar ones, and then some more, and then some more, till everything is part of the cluster. So this picture can also be converted into this pattern. Whatever distance you see between, let's say, A and C, A and D, and so on, that has been depicted on y-axis. So maximum distance is 0.25 and companies are on the x-axis. So what it means is somewhere here, A and C, the distance between them seem to be about 0.03. So they are the closest ones, so they form first cluster. And then B and E, they are at a distance of about 0.06. So they are the next closest one, so they form the second cluster, and so on. So same thing is depicted in slightly different format. And this diagram that you see, the second one, so this is a very common diagram in cluster analysis, and it's called dendrogram. So we are going to look at some examples, and we'll also make this graph in R. We'll look at one example. So this example involves 22 companies, and these are all like public utilities. And the goal is to find a cluster of similar companies. There are 8 variables which are listed here. On the next slide, you have entire data. This is not really a big data. To create this example, we have used a smaller data set, but there are 22 companies and these are all variables. How do we classify these companies, 22 companies, into different clusters based on these 8 variables? So that's the challenge, or that's the goal. You will notice that looking at these numbers and trying to figure that out is not easy. You may be able to look at maybe 2 variables at a time and see what's going on and try to group them. But when you have like 3, 4, or 8, and sometimes in realistic data, like I have seen a data set which has like 1,500 variables. So we need algorithm, we need a computer to do it. It is not possible to do that by just looking at the data or sitting with the calculator. So if we keep it simple for the time being, we just use 2 variables, cost, sales. We are looking at fuel cost, last variable, and sales. Once we make a scatter plot, just looking at it, you can see 3 groups form. Like there are some companies here, low sales, but high fuel cost. And then there are some group of companies with high sales, low cost, and something in between. So roughly 3 clusters can be seen by eyes. Now extend this to more than 2 dimensions, because scatter plot is just 2 dimensions, X and Y. So we could do it by eyes, but if I make a scatter plot such that all 8 are involved, so that is going to be very complex. Just with 3, we'll have like 3 dimensions. So it's going to be difficult. So multiple dimensions require some formal algorithm, and that algorithm needs a measure of distance. Like how do we decide that company A and company B are at what distance? And we also have to have a way to use this distance measure in forming a cluster. So 2 popular algorithms are hierarchical and non-hierarchical. So we are going to look at both. So for hierarchical, we'll start with like one example, and later on we'll see one example of non-hierarchical. So there's a method called k-means clustering, which is very popular. We don't look at like hierarchy, but we decide beforehand that we want 3 clusters, and we tell the algorithm that we need 3 clusters, and then it will try its best and then suggest, okay, these are the 3 clusters which make sense. So hierarchical clustering is of 2 types, again, agglomerative and divisive methods. Now, what is agglomerative method? Very simple. You treat each company as its own cluster. So if I have 22 companies in my data, So start with thinking that I have 22 clusters. And then you keep on joining records or those companies which are closer to each other till you are left with one big cluster that includes all 22 companies. So start with one, and by the end of this process, everything is a part of one cluster. So this is the most popular one. Now this is opposite, divisive method is opposite of that. You start with one big cluster and then keep on breaking till you reach like a stage where every company is its own cluster. So totally opposite direction. Now the question is like, how do you measure a distance between two companies? Like our data has 22 companies. So for measuring distance, there are two methods. One is between records, like between companies. And another measure we have to make or do is between clusters. If I have two clusters, then what is the distance between those two clusters? This distance measure is important because this is needed to decide whether a company or record will go to a particular cluster or not, because that will be decided based on how far it is from the cluster or other companies. So we need between record and between cluster measurements. The most popular method of measuring this distance is Euclidean distance method. This is like the same method that we use for measuring two dimensions on or maybe third dimension on a right angle triangle. So Pythagoras theorem. This is based on a similar idea where you take the square of difference between 2 points and keep on adding them and then take the square root. Because we are using a computer algorithm, we don't have to do these calculations like manually. This is already baked into those algorithms. But one problem is there. What happens is when you try to measure distance between 2 points and square it, raw distance measures get influenced by the scale of measurement. So let me give you one example. This sales, I think, is in millions of dollars. Arizona has 9,000 or $9.077 million sales, whereas Boston has 5.088 million. Now, the way they are written, if you take a difference and square, so the difference is going to be very big. So roughly square of 4,000 and you have a huge number. But if you take difference for fuel cost, 1.5 minus 0.6, that's almost like less than 1. So even if you consider 1, square of 1 is 1. So here the distance is in terms of like square of 4,000. And in this case, you get something which is close to 1. So the problem this creates because of these differences in big numbers and small numbers. So if we don't take care of that, the bigness of the number or smallness of the number, it is almost guaranteed that your cluster analysis will be dictated by this one variable, which has like much bigger numbers compared to others. And variable which has like, I guess, like fixed charge and fuel cost. So their contribution will be almost negligible in comparison to sales. So it's not very fair. We have to have an algorithm which is fair to all 8 variables and allows them to exhibit their contribution in cluster formation. If we leave everything as it is, there are many variables whose contribution will be suppressed or totally masked by sales. So that's not a good thing. As analysts, we have to create a level playing field for all these players so that nobody gets like undue benefit or nobody is penalized because they are small guys or small variables. So that's the problem which is highlighted here. And solution is very simple. Anytime we have this kind of issue, what we do is we normalize the data. We standardize the data. And standardization is very simple. If I go back, so what we do is we find average of each column and also standard deviation of each column. So how to standardize, for example, sales? So we'll do 9077 minus average of sales. and then divide by its standard deviation. And that we do for each variable. So fixed charge, we find the average and subtract that number from 1.06 and divide by standard deviation. So that's how we normalize data. So for example, normalized score for Arizona, where sales was 9077. This is average and this is standard deviation. So we get 0.046. So these normalized values always have mean of, average somebody said 0. And what about standard deviation?
1.
1. So that's what is the normalized variable. So after normalization, whether it is sales or fuel cost or fixed charge or cost, now everybody has an average of 0 and everybody has a standard deviation of 1. So that's how we create a level playing field for all these players, so that whatever they can bring to the table in terms of contribution to cluster formation, so that will be very clear. It will not be that one variable, because it's like very big and it has a loud voice, it suppresses everybody in the meeting and nobody else's views are heard. Basically, normalizing in a way democratizes the whole process and every variable's voice gets heard. Now, when we measure distance, there are obviously same thing can be done in so many different ways. And there are many metrics that people use. I have depicted just 3 ways of measuring distance. Now, for example, this is Portugal and this is France. Now, how do you measure distance between France and Portugal? One way is you look at the point which are closest to each other from each country. This is the point in Portugal and this is the point in France. And then you measure what is the distance between these 2 points. So that's one way. It's called minimum distance or single linkage. Similarly, you can do extreme points. Go to the farthest point in France and Portugal and measure that length. So maximum distance. Or take a centroid, find the center of gravity of this irregular structure. So find what is the centroid value, and from that point you measure the distance between 2 places. So these are like popular ways of measuring distance between clusters. You can think of France as one cluster and Portugal as another cluster. It is difficult to say which method is better, because when you do the cluster analysis, typically what we do is we try all the 3 methods and see which one makes more sense, which one gives better results, and then select that one. So we may not know beforehand because it may vary from data to data. We'll try actually maybe 1 or 2 and see what happens with our data where we have 22 companies. So hierarchical clustering algorithm, it may seem very complicated, but there are only 3 steps. So you start with n clusters, and step 2, merge closest records into one, and keep on doing this till you reach like one big cluster that has everything. And dendrogram is the best way we can visualize this whole process. So this is a distance, and these are all 22 companies. And we find that company number 12 and 21, they have the minimum distance. So they form first linkage on this dendrogram. And this graph is using average linkage method of measuring distance. So how do we read this dendrogram? If you draw a horizontal line, you can focus on, let's say, green one first. So it is about at a distance of 3.6, and it cuts this line here. So this becomes one cluster, and then it cuts this line. So this becomes second cluster, like company number 2, 22, 4, 20, 10, and 13. They are the members of second cluster. And then this one. And you'll also find there's one company, 17. So that's like an outlier. It's very different from all others. And it could not find any place in any of the clusters till a distance of 3.6. Same thing with number 5. And then the last one, consists of companies like 8, 16, and 11. So we have 1, 2, 3, 4, 5, 6 clusters at a height of 3.6. Now, if you focus on red line around 4.6, so at that height, the first place we get a cut is here. And that's a very big cluster. So many companies in that cluster. And the second one is very small, only 1, 2, 3 companies in it. So one thing is very clear. If you draw a horizontal line at a lower distance, you end up with more clusters. If you draw this horizontal line at a higher distance, you get fewer clusters. And at the two extremes, like if you are at 0, then all 22 companies are separate. So you have 22 clusters. And if you are at 5, then everybody is in the same cluster. So you have one huge cluster and all 22 companies are part of it. So this is actually exploratory method. It doesn't tell you like at what distance you get best clusters. It is up to you. It is up to the application area where this is being applied. It is up to the kind of data you have and how you are going to use this method later on. So it depends on all those things. It only presents you the complete picture, and then given the situation you handle, how many clusters will make sense. After we make clusters, we have to actually validate, because we don't want to take chances. Who knows, second time we do analysis and we get totally different result. It may confuse people. One way to validate is interpretation. Obtain meaningful and useful clusters. It may happen that random chance can often produce apparent clusters. And another problem is you use one method, you get one cluster formation. You use another method or measure of distance, you get totally different outcome. How do we do that? How do we interpret correctly? So the best thing is do some summary statistics, like find out averages in every cluster for each variable and see what it is trying to say, whether it makes sense. Also look at variables which may not be in the cluster, because in cluster analysis, we always use quantitative variables. We do not use qualitative. So sometimes people bring qualitative variables and see whether cluster makes any sense in terms of qualitative variables. Another thing we do is label the cluster. So for example, this cluster, they have labeled as high fuel cost, low sales. So that's a label or name given to that cluster. This is low cost, high sales, and this is in between. Another way you could do is you can come out with some creative names, like during last recession, when we had this financial crisis, there were like mid-sized companies, there were subprime losers. So you could have categorized those financial firms in different categories or clusters like this and put a label to them or give a name to them. Validating cluster also could involve stability, checking whether cluster formation is more or less stable. And the way we do this is we split data into two. Actually, this data is very small, only 22 companies. But let's say if you have more data, break it into two and then see if it repeats with each data set or not. Separation, check ratio of between cluster variation to within cluster. If there are like two clusters, so within the cluster, we want less variability because we want the companies within one cluster to be very similar to each other. So we want less variation. But when it comes to like two clusters, we want maximum variation. So they should not be like overlapping with each other. They should be separate, very clear. So we want between cluster distance to be more. One way to combine those two ideas is have this ratio of between divided by within. Obviously, it should be higher the better. Now coming to second type, non-hierarchical. As I said earlier, the most popular method is k-means. And we actually start with k here. We say that, okay, we want 5 clusters or we want 3 clusters because we know that market segment, if we go beyond 3, if we have to do marketing, it will be difficult, more expensive to do that. We may have some idea beforehand and we may tell the algorithm, okay, we need 5, we need 3. So whatever makes more sense. So once you do that, once you choose K, Then this algorithm will separate your data in K clusters. And then it starts performing some calculations, and each step it will move one record to the cluster with the closest centroid, and then keep on doing this till moving a record will increase within cluster dispersion. So within the cluster variability, when it starts to increase, it is going to stop. We are going to see all this in action using actual data that you saw on that slide. Download this utilities.csv. It's a small file, 1 kilobyte, so it should not cause any problem. I'm saving this on my computer in downloads folder. And another thing you should do is go to this link, R code on GitHub. So if you go there, there are a few things you may find useful for your future. So basically I have compiled the top 10 machine learning methods. I also call it like must know machine learning if you are going into any kind of analytics related field or anywhere you are going to work. If you want to apply these machine learning methods, I think these 10 are the most important ones. One of them you can see here is cluster analysis. Click on that, and then you have the entire code. So I will suggest simply copy and paste this into your RStudio. Once again, if anyone missed, how did I reach here? So you see this page, right?
Yeah.
Yes.
Okay. Then I went to cluster analysis, and I'm just copying and pasting this code into RStudio. So let me stop here and share RStudio screen. Paste. So everything comes RStudio without a problem. So if you're ready, run the first line, and my file is under downloads, utilities. So I open it and I can see my data with 22 observations, 9 variables. So this is the same data set, Arizona, Boston, Central, and sales 9077 and things like that. Structure of the data. So company name is obviously a factor variable. It's not a numeric variable because it's text, Arizona, Boston. All other variables are either numeric or integer. They are basically quantitative. And for cluster analysis, we need quantitative variables. We cannot use qualitative. So it's good we have 8 variables which are quantitative. When you have any data, if you want to look at first few rows, do head, and it will give you first 6 rows. Because if you are dealing with big data and let's say you have 1 million rows, you don't want to look at entire 1 million. You can just do head and get first 6 rows. If you want to look at last 6, you can do tail. So it gives you last 6. Now, if you do pairs and my data 2:9, you can run this and it will do a pairs plot. So this is called pairs plot. Basically, scatter plot for all possible combinations of 2 variables. So this is fixed charge versus ROR. So it looks like linear pattern. This is cost versus ROR. So like more randomness. Another thing you can do, like what we had seen in one of the slides, we can pick up 2 variables, fuel cost and sales. Fuel cost and sales, you can see these two have this kind of pattern here. So if we run this, this is how the scatter plot looks. So you can see visually there's one group here, and another group somewhere here in the middle. But in that plot, we also had name of the companies. So if you want to include labels, so you can do that using this line where you have to specify that this is for these 2 variables, and then you want the labels, and that label will be name of the company. So run that. If you feel this positioning is not good, you can always change this number. So if you do 1, so I need to plot again previous line, otherwise it will overwrite. So you see 1 means bottom, the name of the company will be below the dot. If you do 2, it goes to left side. So basically it moves clockwise. 3 will put it on the top of the dot, and 4 will make it towards the right. So whatever works, we can use that. Next group of quotes, basically we are normalizing the data. You saw normalizing is very important when you do cluster analysis. If you do not normalize, then it is going to create problems. You may not get a true picture, or the clusters that are formed may not be dependent on those 8 variables. Maybe just one variable plays a very dominant role, and all the clusters that are formed are because of that variable. For normalizing, what we'll do is, because we cannot normalize company name, it's a text data. So we have to deal with only quantitative variables. How do you do that? You do that by specifying rows and columns. And we specify row and column by using these square brackets. So for example, I'm just typing in console my data, and then if I use square brackets, and if I say, so for row, let's say 2 rows, and for columns, if I say 1 to 9, so all 9 columns, and hit enter. So it will bring the second row and all 9 columns. If I want, let's say first 3 rows, I can do first 3 rows and first 9 columns like this. So using a similar thing, if from within my data, I do not want first column because that's a company name, text data. So I could have written just -1, but sometimes you may have data where not only column 1, but you also need to maybe remove column 5, column 8, because they are qualitative. So this is how you can do. I will later on rerun, but let me give you one example. Suppose I don't want column 1, column 5, column 6, and column 9. So basically I only want 2nd, 3rd, 4th, and then 7th, 8th. If we select this part and run, so you can see the other columns are excluded, only the remaining columns are there. But we'll return to our removal of first column only and save that in Z. So if you check Z, you can see now we do not have any company there.
Professor, this is similar to years, right? I think we could do this with negative years.
Not similar to that. Here we are just removing one column.
Right.
And then storing the resulting, like this data is part inside Z now.
Right.
You can check here also. So the only difference between my data and Z is 8 variables and 9 variables.
Exactly.
Now the next line, what it does is it uses apply function on Z, because I have used Z here, and it calculates mean for each column. Now, how do we know it is calculating mean for column? Because we are specifying 2. If you use 1, let me write down here. So 1 means row and 2 means column. In this situation, I want to calculate mean for columns, so I'm using 2. But there may be some situation where you want to calculate row wise, you can use 1. So run this and select means, just check, because whenever you do something, you should know what's going on. So only select means and run. So what do we have? We have average for fixed charge. We have average for ROR. So basically it added all 22 values for the first column and divided by 22. And that's what is 1.114. Similarly, this is the average for this second column. Now we use similar function just like the previous one, but instead of mean, we calculate standard deviation and store it in SDs. So run that and check your SDs, and you'll find that it contains all the standard deviations. And you can see like average for sales is 8,914. And obviously standard deviation also is very big, 3,500. And others are very tiny, 1.1 and 0.5. Having calculated these two, means and standard deviation, we use scale function. Basically, scale is to normalize. So we supply z values and we tell scale that center should be means, like subtract means and divide by standard deviation. So that's what it is going to do and store everything in NOR. So let's run that and check NOR. So now you see the values for each variable. So sales, which used to be like in thousands, 9,000, 8,000. So it has brought back to range of like plus minus 3, which is applicable to standard normal distribution. So these values are most likely to vary between -3 and +3. The value which is close to 0 is close to mean, obviously. So for example, this -0.2 is closer to the mean for fixed charge compared to this one, which is like 2 standard deviations away from the mean. The main point is that everyone is now within that range of ±3. Everybody has been standardized. We now use this data, not the original data, but this data to find distance. And to calculate distance, this is the formula. What are we calculating? Remember that formula for Euclidean distance. So that's the formula that is being used. Let's run this and save this in distance. So all possible distances are now calculated. And if you want to look at distance, just select and run. I'm going to make some room so that we can see everyone on the same page because it has a lot of decimals. So let's type print distance and digits equal. So let's try 3. Okay, so now we can see everything on one screen. And don't worry about warnings in R. Warnings is okay. It's a friendly warning. It's not an error. So we see everything on this one screen, all possible distances. So it is a lower triangle and there's no point in filling the upper triangle because it will be redundant. Same value will be repeated there. So distance between company 1 and company 2 in terms of 8 variables now is 3.1. I see some big differences, like let's pick up one big difference. So there's one 6.46. This could be the highest unless I see anything bigger. So maybe this is the maximum distance. So this is between company number 5 and 11. So company 5 and 11, let me check. So my data, so we want 5 and 11th row, comma, if I leave it blank, that means I want all columns. So this is what we have. And you can see, for example, 5th company has a sale of about 3.3 million and 11th company is like 17.4, more than 5 times, almost 6 times difference. Similarly, nuclear, Nevada has like 0 and first company has 15.6. So almost like all variables except maybe load, which is like 1.2 and 51.5. So these numbers seem very close, but everybody else seem to be quite different. So this distance between 5 and 11, you can see, captures those differences in terms of 8 variables. If you look at 2 companies which are very close to each other, where the distance is low, so there is 1.88 somewhere here. In fact, 1.41 that I can see. There may be something smaller, but let's go with this one. So this is a 10th company and 13th company. They seem to be very close in terms of all 8 variables. So 10 and 13. So let's check. Sales 6.4 million and 7.1 million. So that's very close to each other compared to this like 5 times difference. 53.7, 53, 197, 199, 1.12, 1.15. So in terms of most of the variables, it seems like these two companies are very close when we consider all 8 variables. This is just to give idea, but obviously we cannot do this manually and figure out like which companies are close, and even after getting a distance, we need some algorithm or some easy way of bringing these companies together which have low distance and separating those companies which have big distance. So that's what we do with hierarchical agglomerative clustering. And in R, doing hierarchical clustering is very easy. This distance that we calculated, we apply this function called hclust. So h is hierarchical and clust is clustering. What we'll do is we'll save this in mydata.hclust. Let's run this line. And to plot, it's very simple. Simply plot this and we get dendrogram. So these companies 10 and 13 that we thought are very close to each other, you can see in this picture 10 and 13 are amongst the closest companies, and 12 and 21 are also very close to each other. And we had 5 and 11. So you see 5 is somewhere here and 11. So these two people, they are like enemies. They will never be together. They will always be part of different clusters. So if 5 goes in one way, 11 is expected to go in other way. If you look at a height of about 5, so we get one cluster here, second cluster, third cluster, and fourth cluster. At a height of about 5, we get like 4 well-grouped clusters. These numbers that you see at the bottom, they are the number of the companies. So this is the third company, this is the 9th company, 6th, and so on. But sometimes people want to look at, instead of referring back to that table and then checking, okay, company number 3 is this company or 9 is this company, you can plot the name of the companies on this graph itself using this line. So you can say Central and Kentucky are together, Boston and Virginia seem to be close to each other, and so on. If you do not like the fact that some companies seem to be hanging in the air, like you see this one is somewhere here, this is at the bottom, a lot of ups and downs. If it doesn't look good to your eyes, you can make them hang wherever they want to hang, like wherever you want them to be hanged. So if I want to hang them at -1 distance somewhere here, I will run this line, and now every line is extended to -1 and everybody is aligned on the x-axis. Now another thing is, you look at the bottom, it says complete. So it has used complete linkage method, but we have seen earlier that there are other methods also, like there is an average linkage and there is minimum distance. So that type of linkage, single linkage, but default is always complete. For any reason, if you are not happy with this pattern that you get, you can try a different distance measure and get a new pattern. So for example, here, if I run, you see the method is specified as average now. So if we run and plot, you get this pattern. So the distances are obviously different. Like you see this arrow here in the 4th window. If you go back, you are looking at a distance up to almost 6 and even more than 6, because it was complete linkage. You are going like farthest away, but average distances are obviously closer. So the maximum distance is about 4.5. If you draw a line at 3.5, you get 1, 2, 3, 1, 2. So 3.5, so 1, 2, actually 3, 4, 5, 6 clusters. And I would say this is not better than the previous one, because in 2 cases, it was not able to find a place for them. There's no home for 5 and 17. So these are like 2, almost like treated as outliers. So they have to stay out of the group. But if you look at previous one, so every cluster had sufficient numbers, like around here. First cluster has 1, 2, 3, 4, 5, 6, 7. second one has many, and third one has at least 3, and then this one has many. Here at one point you have too many companies, and at some point you have like too few. So that's not a very balanced kind of picture. One more thing you can do in terms of code and representation. I'm going to add a line here, and there's a function called rect.hcclust. So what it does is it will draw a rectangle. So visually you can see where your clusters are. So use that, and let's copy and paste name of the cluster, mydata.hclust. And let's say we want 5 clusters. So draw rectangles in such a way that we end up with 5 clusters. So I would say k equals 5 and run. So you can see 1, 2, 3, 4, 5. So it will automatically find out at what height you get 5 clusters. If you say 3, I'll have to run this again. And then it will draw 3 boxes. Obviously, this is not a good cluster because you have like one cluster which is almost all the companies, and then one cluster which has only 1, and first one has only 3. So very skewed kind of clustering. But the idea is like with these rectangles, you can draw a box. If you don't like red, you can always change your color. So for border, suppose you want green, then we can get green. So you can choose whatever you like. Just as an example, suppose these are the 3 clusters. So we know 11, 8, and 16 are in one cluster, 5 in another, and everybody else in the third cluster. If we say cut 3 and look at a table, it just tells us that first cluster has 18 members, so it has 18 companies. Second cluster has 1, and third cluster has 3. So let's use a previous one where I think clustering was better. I'm going to run this line again and put a rectangle with 3 clusters. Instead of 1, now we have 5. So 14, 5, and 3. But what is of importance is what exactly this cluster is representing. That is very important because right now we only know that, okay, based on some algorithm, based on 8 variables, this is what we get. But what exactly is making this cluster? What is the contributing variable? We need to characterize. So this word characterizing comes from character. So just like a character of a person, clusters have their own character. We need to characterize and figure out what is going on. And that we do by finding average for each variable in the cluster. And that we can do using aggregate function. So if I run this, let me make some room. This is what we get. So remember, this is normalized averages for 3 clusters. A good thing about normalized is that we can compare across and figure out which variables are contributing more to cluster formation and which variables are contributing less. Variables that contribute more will have bigger average differences. So for example, if you look at this cost, maximum value is 1.3, minimum is 0.3. So the difference is about 1.6. If you look at fixed charge, 0.3 and negative 0.6. So the difference is about 0.9. So we can say this variable cost contributes to this cluster formation more than fixed charge because it has a difference of 1.6 compared to only 0.9. Similarly, if you pick up a load, 1.3 maximum, minimum, almost negative 0.5, so 1.5. So load is a bigger contributor now. compared to even cost, because the difference is 1.9. Now look at the sales, maximum 1.8, minimum 0.6. So if you say 0.7, so roughly difference of 2.5. So sales seems to have a large sales even after normalizing in formation of these clusters. So this is how we can see. But now how do we characterize? So what exactly is going on in cluster 1? If sales is a big player and if load is another big player in cluster formation, then cluster 1 has low sales, actually medium sales, because this is high and this is the lowest. So cluster 1 has companies that have medium sales and somewhat lower load values, because this is roughly 0.4, this is 0.5, so not big difference. And then if we pick up another strong variable like this one, 1.2, so almost about 2.2 difference. So medium fuel cost also. So cluster 1 is characterized by medium load, low sales, medium fuel cost, because low is for cluster 3. The attributes for cluster 3 are very low fuel cost, but very high sales, very high D demand, and also very high cost. Whereas cluster 2 has very high load, but very low sales. So this way, these means for each cluster can tell us what exactly is the character of each cluster. And after that, if you still want to compare them in terms of actual values, you can always run this next line and you get actual averages for the 3 clusters. So you can see there is a big difference between sales in cluster 1 versus cluster 2. So cluster 2 sales are almost 2 times than the companies that are in cluster 1. Any questions?
I have a question.
Okay.
I'm not sure, like, okay, we are doing all this stuff. What is the purpose, after all? We aim to achieve by doing this method.
So by doing clustering, some of the examples that I gave in the beginning, like if you have investment companies, if you have to propose portfolios to customers and you want to group companies based on certain characteristics into certain groups or clusters, let's say your portfolio has like one type of companies which is very risky. And based on various parameters, you find that there are 15 companies you will propose to a customer that you could choose something from this. And then there could be a group of companies which are belonging to like safe. You don't make too much money, but maybe you get very good dividends. And based on various parameters, you may identify 25 companies that you can propose to a customer that probably you can choose something from this and you'll be fine. Having those portfolios and like different clusters will also ensure that the customer doesn't end up investing everything in risky companies. So if somebody is more risk taking, maybe 80% risky, and they want like 20% in safer companies, then they can choose using those clusters. So this clustering will help in guiding them in the right direction.
So the general idea is that this method will help us group companies in a way that they represent similar qualities?
Yes.
Okay.
So that's the idea. Yeah.
Okay, thank you.
Yeah, no problem.
Yeah, just to add on to this, I think marketing uses clustering techniques a lot, right? To cluster customers and then try to make marketing strategies and things like that.
Yeah. So marketing is a big user of this method. Marketing teams, they analyze this data in so many different ways to group customers into different clusters. Obviously, depends on business what they are looking at. So whether they may be looking at income or family size or some other parameter, age, but they can use that to cluster and make some strategies. Once like they identify proper clusters, they can maybe customize their marketing for each cluster. So just to have a simple idea, like let's say one cluster is mainly based on age and younger group. So the type of advertisement or marketing tools they will use will be different compared to a group of customers who are maybe like higher age group or a different income group. It can help to implement different strategies. Okay, so, but these are some tools that basically, there's no right or wrong answer, I would say, but these are the tools that people can use and combine this with their judgment. So once you have a cluster, sometimes we want to know how good a job we have done in forming these clusters. And a plot that can help in that is called silhouette plot. It is part of a cluster package. If you don't have it, you may have to install it. If you run this line and if it gives any error, make sure you install it. Otherwise, you should be able to plot and get something like this. So this is with the same data and same number of clusters, 3, same type of cluster method. So we have 14 companies in one cluster, 5 in second, 3 in third. If you look at first group and compare it with second group and third group, you'll notice that the bars are quite high in second cluster and third cluster. So if this metric, whatever way it is calculated, we don't go into that. But if silhouette width is on the higher side, that means these clusters are healthy. So the cluster memberships, it's good actually. But if you look at the first one, there are some members that fit in that cluster nicely. But there are also some members which are a bit doubtful. And in fact, company 2 seems to be an outlier in this group. Somehow it has been forced into cluster 1, but it's not really that cleanly into that cluster. If you think of a cluster in terms of dots, each dot representing a company. So there are like 13 companies. Those dots are closer to each other. But then there's one dot which is slightly away. And that is company number 2, which doesn't seem to fit nicely here. It's okay to have 1 or 2 companies like that. But if we have too many, that means there is a problem. So that means try something else. Try complete linkage, average linkage, or single linkage, or maybe k-means clustering. So basically the idea is don't use that, go with something else. Or maybe increase the number of clusters. Maybe 3 is too restricting for many companies, and there are some 4 or 5 companies, they want to have their own group. So then try 4 clusters and see if things improve. Another plot that we typically do, usually we do this at the beginning of any cluster analysis, is called Scree plot. I would suggest just run the lines and then I will explain to you what it means. So you should get a plot something like this. So it uses the same data, obviously, normalized data, and does some calculations like within sum of squares, and then this within group sum of squares is plotted on the y-axis, number of clusters on x-axis. This is like 5, 4, 3, 2, 1. First dot means if all 22 companies are in one cluster, then what will be in a way like variability within the cluster. So obviously it will be very high because not every company is close to other companies. So within group sum of squares will be high. If we break the entire data into 2 clusters, these 22 companies go into 2 clusters. So now obviously the variability is going to come down because those companies will be closer to each other. If you do 3 clusters, within cluster variation will be even less, and it is going to keep on decreasing because every time you make more clusters, so the members in the clusters will be closer and closer and closer, and the variability will be less. But how to read this is we look for a place where there is a bend, like knee. So when you go from everybody in the same cluster to 2 clusters, there is a big drop. You can see this line is long. 2 to 3, again you get a good solid reduction in within sum of squares or within cluster variability. Again, very good. But After that, the improvement is not really very encouraging. Like when you go from 3 to 4 clusters, this becomes very small. And after that, you see diminishing returns, like this length keeps on becoming smaller and smaller. So ideally, I would say the number of clusters should be somewhere around this knee. And because this looks like some odd thing happening, so either it could be 3, 4, or 5. But beyond that, you see this length and this length, this is almost half of this. So we are not getting any big improvement by increasing number of clusters. And with 22 companies, there's no point in having like 10 clusters, maybe 2 companies in every cluster. That's not a good idea. With 22 companies, we don't want to have too many, and we don't want to have too few also. This picture basically gives you an overall trend of what is going to happen with if you go for 2, 3, 4, 5 clusters. And then looking at this, you can get some idea. So if you have to experiment further with the dendrograms and other things, your experiment should basically focus on either 3 clusters or 4 or 5. There's no point in having only 2 or having 6, 7. So you can ignore that and focus on something narrower. So that's the idea of Scree plot. So typically you may do this at the beginning of cluster analysis. So this is another tool that can be handy when you are exploring cluster formation. Coming to k-means. So that is like a non-hierarchical clustering. See, this set.seed fixes the randomness. If we don't run this, what I get and what you get will be very different, because the algorithm will start randomly at some point. But if we force that randomness to start at a specific place, then we should use the same number. Like if I'm using 1, 2, 3, and if you are using 1, 2, 3, then we get a similar result. Otherwise, we get totally different cluster formation. So I would suggest run this line. And then for doing k-means clustering, very simple. Your data is NOR. And let's say we want 4 clusters. So we specify 4 and save the results in KC. So run this and you are done with k-means clustering. If you run KC, select KC or maybe type KC, where we have stored everything, and run. So it's going to give you this, everything that it has done. K-means clustering, 4 clusters, and this is the cluster size, number of companies in each cluster. And then you don't have to separately find out like what are the averages using aggregate function. It automatically gives you that output. And then you can characterize clusters. It also tells you first company belongs to cluster number 2. Second company in the data belongs to cluster number 1. Fifth company in cluster 1, and so on. You also get within cluster sum of squares, something like this, within group sum of squares in cluster 134. Now, if you are following with me, can you tell me whether a good cluster is the like one where within cluster sum of squares is high or low? For a good cluster, what should you have? Should this number be high or low?
Low.
So I have some answers like low. So that's right, like within cluster, all these companies should be closer to each other. So this number, if it is low, it means good cluster formation. Out of 4 clusters, third and fourth cluster, they seem to be doing really well. The numbers are lower compared to first 2 clusters. We then have between cluster variability divided by total. Between means if 2 clusters are there, if they are close to each other, that's not good because there may be an overlap between 2 clusters. That's not a good cluster formation. And if they are far away, there's no overlap. So that means the cluster formation is good. So if this number is high, which means the 2 clusters are further away, that's a good thing. If this number is low, that means they are closer to each other. That's not a good thing. It gives us some idea about the quality of the clusters. Why this is important is if you are not happy, let's say if you just want to explore and see what if I go with 3, because if I make 4 clusters, my marketing will be very expensive, because then I have to have like 4 marketing strategies, and I need to use like different tools, and the money I have to spend on doing that marketing, creating the marketing brochures to cater to like 4 clusters will be more. But if I go with 3 clusters, I'll have to spend less money because I can design only 3 marketing material, and then I can send them. If you run this line and run KC, so now we have 7, 12, and 3. Second cluster is bigger. Within, which should be low, in second cluster, the value is really high, 76. In fact, earlier highest value was 34. So now we have a situation where within variability has increased more than 2 times. That's not a good indication. Similarly, this number that should be high. So with 4 clusters, we had 52. With 3 clusters, it has dropped from 52 to 32. So a big drop. It has given away 20 points, which means like earlier clusters were like separate nicely. And now there's a possibility that they are very close or there may be some overlap. If we go to 5, not here, last line. If we go to 5, if I run this, run this, run this, this is the outcome with 5. And 1 has only 1, 1 has 3. So when you increase number of clusters, obviously within cluster variability will come down. So you can see this is better. And between cluster variability has gone up, which is also good. But the key point is, did we achieve a lot? From 52, we have gone to 59 or 60. So we have gained 8 points in terms of separation between clusters, which is not as high. When you go from like 3 cluster to 4 cluster, there was a jump of 20%. Now that has come down to less than 8% jump. So obviously we are not gaining too much. If it is a marketing application, and if having 5 clusters is going to increase the cost by 20% or whatever, so it could be a choice between like number of clusters as 4 or 5. And also your cluster formation is such that there's one group where there's only one company. In this case, probably you may tend to go towards 4. Now, if you want to visualize this, let me make a plot. There is a function called CLUS plot. My data. So let's use our data as it is, and we'll do the clusters. Let's do some beautification of this plot, and then I will tell you what it is. Color equals true. Let's also shade each cluster. Let's also put labels. So the last one I ran was actually 5. So I'm going to go back to 4. So let me run these again. Okay, so these are the 4 clusters. Like we got some idea actually looking at these numbers and percentages. But now if you see visually, this is cluster number 3 and this is cluster number 1. So they have a good separation between them, and cluster 3 and 1 are also well separated from cluster number 2 and 4. But clusters 2 and 4, they seem to have overlap. One has to see like whether that makes sense and whether we should still try and do 5 or maybe 3, because visually we can see 2 and 4 seem to have some overlap between them. So what you're seeing this through numbers, you can also see visually and very easily see where cluster formation is good, where the variability within cluster is good, and how is the variability between clusters. So this could be a good tool to visualize your clusters. There are actually many other methods of clustering. I have only talked about non-hierarchical and k-means clustering, but there are other methods also available, but these are like most popular ones.
Yeah, I have a question. What does, so in this class plot, what does the X label and Y label mean? It says component 1 and component 2. What does it mean exactly?
Yeah, so what happens with clustering is, as we discussed in the beginning, when you have 8 variables, you need a plot which is like more than 2 dimensions, and it's very difficult to figure out what's going on. So what this plot does is, it does some kind of, I don't know if you have heard of a principal component analysis. Basically, it picks up 2 main components out of all possible components. And the idea is that component 1 and 2, so they should capture most of the variability in those 8 variables, and then flatten them on a 2-dimensional plot so that it is easier for somebody to and look through their eyes and see what's going on, which is not possible to do when you have something which is like 8-dimensional. So if you look at the bottom, component 1 and 2, obviously like there's component 1, 2, 3, 4, 5, and if you add all the variability in those components, it will add to 100. But just these 2 components. Now, what is a component? Component is a combination of all 8 variables. They capture almost half of the variability in the data. Almost 46% of the variability is being explained by just these 2 components. So obviously, like we are not presenting the entire picture in terms of all 8 variables and entire variability. We lose something, but what we gain is we are able to look at and visually see what's going on. So with some loss of information, at least we can interpret visually and see what's going on. So that's what like these components help us to do. In the background, this cusp plot is doing a principal component analysis and presenting us results based on 2 components, 2 main components or principal components, which contribute maximum. Like the total variability they are able to capture is almost half. So that's the idea.
Thank you, Professor.
Professor, when we try to do this for 3 groups, we also have some overlapping between groups, right?
Let's see. So we do 3 and we repeat. This is the characteristic of the data. These tools cannot make them separate. It can only like present the reality, okay, this is the case, and it's not possible to separate on a 100% basis. But you can see like these 2 clusters, I would say overlap is slightly better than the previous one, right? Slightly better, at least majority like of the companies are still outside. You have 1, 2, 3, 4, 5, 6, 7, and there are some on the borderline. But here you have 1, 2, 3, 4, and majority of them are trapped in the overlap. In this plot, cluster number 2, companies are represented by these triangles. So 1, 2, 3 triangles also overlap with these blue ones, which is represented by this cross. And 1, 2, 3, probably there's one cross here also. So there are 4 companies that overlap with cluster 2. That cannot be held. It's not that we can separate 2 clusters if the data wants them to be together. But it's a good idea to try 3, 4, and 5 and see what makes more sense, what you're losing, what you're gaining. The only thing is that in principal component visualization here, you do lose remaining 50% of the variability. So this is in a way not complete picture because you're covering only 46% of the variability in the data. There is some give and take, and then it's subjective. You may come out with one way. You may think that 4 will make sense. Somebody looks at the same thing and may feel that probably 3 makes more sense. It may vary from person to person. If no other questions, then I'm going to stop here, and good night to all of you.
Thank you, Professor. Have a great night.
Yeah, you too.
Good night.
Thank you.